Welcome to Semester 5 Mathematics at Delhi University. Today we are diving into one of the most powerful and universal ideas in applied mathematics, conservation laws. We will discover how simple, everyday observations about things flowing in and out of a space can help us mathematically model everything from river pollution to highway traffic. Let us begin. Let us start with a simple picture. Imagine you are watching a busy highway from a bridge. If you look at a specific 1 mile stretch, the number of cars inside can only change in two ways. Cars enter from behind or they exit from the front. Cars do not magically appear or vanish. This everyday observation is the heart of a conservation law. It simply states that the amount of stuff in a specific area only changes based on what flows in and what flows out. To translate this into mathematics, we need to define two key functions. First is the density function, which tells us how much of our quantity exists at a specific point in space and time. Second is the flux function, which measures how fast this quantity is flowing past that point. The fundamental principle of a conservation law is that the rate of change of the total amount inside a region must perfectly balance the net flow across its boundaries. If more flows in than out, the density must increase. This brings us to the fundamental differential equation for any conserved quantity in one dimension. The partial derivative of u with respect to time plus the partial derivative of phi with respect to space equals 0. Conceptually, this means that local buildup plus local spreading always equals 0. The variable u is our density and phi is our flux. If the flux changes as you move along the x-axis, it forces the density to change over time to maintain perfect balance. Take a look at this diagram. It visually summarizes the physical domain we are modeling. The shaded blue cylinder is our specific region, stretching from point A to point B. The total amount of stuff is trapped inside. On the left, phi of A, t represents the flux entering the region. On the right, phi of B, t is the flux leaving. The difference between these two arrows dictates exactly how the density inside the blue region will change over time. Now that we have our fundamental equation, let us see it in action with a concrete example. Suppose a chemical pollutant is accidentally dumped into a river. The river flows downstream at a constant speed. We want to model how the concentration of this pollutant changes over time. Since no new pollutant is being created in the water and none is magically destroyed, this is a perfect scenario for our conservation law. To use the conservation law, we first need an expression for the flux. In a flowing river, the flux is simply the concentration of the pollutant multiplied by the speed of the river's current. Here, c is that constant velocity and u is the pollutant density. Multiplying them tells us exactly how much pollutant washes past a specific rock every second. Physically, if the water moves faster or if the pollution is thicker, the flow rate increases. Let us solve for the governing equation. We are given our general conservation law and our specific flux equation. We substitute the flux, c times u, directly into the spatial derivative term. Because the river speed c is a constant value, it does not change depending on your position x. Standard calculus rules allow us to pull it out to the front of the derivative operator. This gives us the final result, famously known as the linear advection equation. It guarantees the pollutant simply rides along with the current without changing its shape. Let us look at a more complex real-world example: traffic flow. Consider a long line of cars moving in a single direction on a one-lane road. Unlike the river, the speed of the cars is not constant. It depends entirely on how crowded the road is at that exact moment. If the density of cars increases, drivers naturally slow down. We want to derive the partial differential equation that models this specific traffic density over time. Based on our description, we can write a mathematical equation for the velocity of the cars. The velocity v depends on the density u. The constant Vm represents the absolute maximum speed limit, like when the road is completely empty. The constant Um represents the maximum bumper-to-bumper traffic density. Notice that if the current density reaches this maximum, the fraction becomes 1, the term in parentheses becomes 0, and the cars are completely stopped in a traffic jam. To find our governing equation, we first need the flux. We calculate this by multiplying the density u by the velocity formula we just established. This flux represents the total number of cars passing a specific street lamp every single hour. To make the upcoming calculus steps easier, we will distribute the u inside the parentheses. This gives us a simple expanded algebraic form of the flux equation, which is a polynomial that is much easier to differentiate. Now we need to find the spatial derivative of this flux to plug into our conservation law. Because the flux depends on density and density depends on position x, we must use the chain rule from calculus. The chain rule states that the spatial derivative of flux is the derivative of flux with respect to density multiplied by the spatial derivative of density. Taking the standard derivative of our polynomial with respect to u, the derivative of u is 1 and the derivative of u squared is 2u. We now have our expression for how sensitive the traffic flow rate is to small changes in density. We substitute this derivative back into our chain rule expression and then plug that entire term directly into our main conservation law equation. This gives us our final answer. This is a non-linear partial differential equation because the term multiplying the spatial derivative depends on the density itself. This mathematical nonlinearity is exactly why sudden traffic jams can form out of nowhere. Now that we have successfully used the fundamental conservation law to model both rivers and traffic, let us take a step back and understand where it actually comes from. We are going to prove this theorem from scratch. We start by defining the total quantity Q in an arbitrary fixed section of our one-dimensional space between points A and B. We find this total amount by integrating the density U over that specific distance. Next, we apply a time derivative to this integral to ask a crucial physical question. Exactly how fast is the amount of stuff inside our section changing as the clock ticks forward? Continuing our derivation, this rate of change we just defined must perfectly equal the flux entering at the left boundary A minus the flux leaving at the right boundary B. This mathematical statement captures the intuitive idea that changes only happen at the borders of our region. Now we use a core concept from calculus, the fundamental theorem of calculus, to rewrite the right side of our equation. We can express the difference in these boundary fluxes as the negative integral of the spatial derivative of the flux. This is a brilliant mathematical step because it converts boundary values into an integral over the entire space, matching the left side. For the final result of our proof, we now equate our two integrals. Assuming our physical functions are smooth and well-behaved, we can safely move the time derivative inside the integral sign. Next, we move all terms to the left side of the equation to combine them into one single integral expression. This combined integral now equals 0. Because we chose the starting point A and ending point B completely randomly, the only way this integral can evaluate to 0 for absolutely every possible interval is if the function inside the parentheses is itself 0 everywhere. This logical conclusion gives us our final derived fundamental differential equation. Before we wrap up, let us reflect on why that nonlinear traffic equation was so important. In mathematics, when the density itself dictates how fast the wave travels, the equation is nonlinear. This explains why traffic waves can compress and change shape, eventually forming shock waves, those frustrating traffic jams that appear out of nowhere. These same nonlinear conservation laws are the absolute bedrock of modern physics, used to design aerodynamic wings and predict flood patterns. Let us summarize what we have learned. A conservation law is a mathematical bookkeeping tool that ensures no physical quantity is lost or gained without a trace. It perfectly balances the rate of change of a quantity inside a region with the net flow across its borders. By defining a density and a flux, we derived the fundamental partial differential equation that governs these systems. You have now seen how this single, elegant principle can model both simple river currents and complex highway traffic. Excellent work today.